Hello, everyone. Thank you for joining us and welcome to the ASTRO 3D ECR Astronomers in Australia seminar series. My name is Dr. Jeffrey Simpson. I am a postdoc at the University of New South Wales in Sydney, Australia. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today, the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we meet today. I'm speaking to you today from the land of the Wallumedegal clan. Our first speaker, Jake Clark, is speaking to you from the country of the Djiabul and Jarawara people. And our second speaker, Stephanie Monty, is speaking from Ngunnawal country. We pay our respects to their elders, past and present, and extend that respect to all First Peoples joining us here today. So why are we here? So this series is facilitated by ASTRO 3D, the ARC Centre of Excellence for All-Sky Astrophysics in 3 dimensions. COVID-19 has affected our ability to travel and present at international seminars this year and last year. And especially for us in Australia, the time zone differences often mean that often meetings are taking place at 2 or 3 in the morning in our time. And this lack of opportunity to network could disadvantage junior astronomers entering the job market. And so what we're going to have today is 2 talks over the course of this hour. Each talk will be 20 minutes in length with 5 minutes for questions at the end. Please save your questions until the end of each talk and feel free to use the chat function to ask your questions if you prefer. And I can read them out from the speakers. These talks are going to be recorded and will be put on YouTube after this for educational and scientific purposes. And by being here today, you're agreeing to abide by ASTRO 3D's meeting code of conduct. And I've already told the speakers this, but because of the limitations of Zoom, I'll actually have to interrupt them verbally in the middle of it with 5 minutes left to warn them about the time. So that's all the housekeeping. So on to our second speaker. Stephanie Monty is a PhD candidate at the ANU specializing in instrumentation and stellar chemodynamics. She is a high-resolution enthusiast who enjoys combining adaptive optics with high-resolution spectroscopy. So Stephanie, the screen is yours.
I wanted to thank ASTRO 3D for being here, or for giving me the opportunity to be here, and also acknowledge the land of the Ngunnawal and Ngambri people that I study on, work on, and basically, thankfully, have access to every day. Okay, just gonna change the view a bit. There we go. So I wanted to talk to you today about MAVIS, specifically about some work we've been doing to look at the astrometric capabilities of MAVIS. So my interest is both instrumentation and science. So I like to look at things from the perspective of how can we motivate the instrumentation and the capabilities of the instrument from the science, and how can the instrumentation inform us what kind of science we can do and what kind of limits we can push. So this is in collaboration with my supervisor, Francois, and several other collaborators, Richard McDermott, Holger Baumgart, Jesse Cranny, Guido, and Trevor. So that's okay. So we'll just start with an overview of adaptive optics. If you haven't seen this before, maybe you slept through this part of Astro 101. Maybe it's not part of Astro 101 yet. So what we want to do here is basically let our ground-based telescopes operate like they're in space. So we want to remove the effects of the atmosphere and take the twinkle out of our stars. We do that through a kind of a complex system. It was first proposed in 1956 and actualized in the 90s. So what this means is that we capture the light from our telescope. We're going to measure how distorted the light is. So how distorted it becomes by traveling through the atmosphere, and then correct that distortion, sort of like a negative interference, using our deformable mirror to correct it to a flat wavefront. So that's taking the twinkle out. And then basically cycle through to try to track the changes in the atmosphere so that we can correct the light in real time. So the corrected light is then sent to an instrument, a scientific instrument. So classical AO delivers near diffraction limited images over a small-ish field of view. That's relative. So small in this case is about 20 arcseconds by 20 arcseconds. Multi-conjugate adaptive optics, which is what MAVIS is a flavor of wide field AO. So this corrects a larger field of view than classical AO. And so your science objects obviously increase based on that. So here's a schematic of MCAO. So where classical AO uses one deformable mirror, one wavefront sensor, and corrects for one layer of the atmosphere. Multi-conjugate adaptive optics corrects for many layers of the atmosphere, creates a larger volume, and what that amounts to is a larger field of view. So to measure the turbulence from the atmosphere, we use reference sources. So we have natural guide stars and laser guide stars. Natural guide stars are natural stars that appear in the sky, obviously just bright stars. Laser guide stars are artificial stars that we create using sodium lasers. So they tell us different characteristics of the atmosphere. LGS we can create on demand, which is nice. NGS we have to rely on the sky to provide. So so MCAO, where classical AO would use one natural guide star and one laser guide star, MCAO uses multiple. So this increases the complexity, but increases our field of view. So the only MCAO system in operation today is called GEMS. So this is the Gemini South Multi-conjugate adaptive optic system, and it operates in the near IR. So GEMS uses 5 laser guide stars, 3 natural guide stars to correct 85 arcseconds by 85 arcseconds. So it's really been groundbreaking in the field, I think, and it's MAVIS's, I would consider it to be MAVIS's predecessor. So here's an example of what MCAO can do for you. So this is GEMS, and this is the field from GEMS, and it's being compared to the blue field here, which is substantially smaller relatively. That's the field of a classical AO system called Altair. So Altair was also a groundbreaking system on Gemini North. So that would just use one laser guide star and one natural guide star. And here you're seeing the improvement between them. So GEMS delivers a similar improvement over a wider field. And obviously when you're seeing limited, that twinkle is blurring your stars, which you don't want. So who is MAVIS? So MAVIS, again, is an MCAO system. It's being designed for ESO, so the observatory on Paranal, specifically for the VLT AO facility. So it's going to feed an imager and an IFU spectrograph covering 400 to 950 nanometers. So here's MAVIS in the context of existing instrumentation and instrumentation that will go on sky hopefully very soon. So you've got the angular resolution. So that's the spatial resolution you can achieve as a function of wavelength. So you see MAVIS occupies this kind of unique regime where it's operating quite blue, and significantly bluer than the ELT, obviously, because that's going to operate in the near IR, at least the adaptive optics component. And we're going to push to higher spatial resolution than HST by virtue of being a bigger telescope. So it's the first ever MCAO system to operate in the visible, which is really exciting for us, but presents many technological challenges. So why do we want to push to the visible? So the spatial resolution is inherently limited by the wavelength you observe at. So the bluer you go, the higher spatial resolution you can achieve. So GEMS operates in the near IR, so that's in the HJ and K bands. So MAVIS will push the resolution higher by a factor 4. That's actually comparable to the 39-meter telescope in the HJ and K bands you can see here. So that's what introduces a complementarity between the two as well, which I can talk about a bit later. So, so what will MAVIS achieve once it's on sky? So we aim to deliver near diffraction limited images. So the diffraction limit in the V band, that's as if the telescope was operating in space, no atmosphere, is 0.014 arcseconds, 14 milliarcseconds. MAVIS will deliver 18 milliarcseconds over a 30 arcsecond by 30 arcsecond field of view. So that's pretty good at the moment, we think. So here's some highlights from the MAVIS science case. So the model for MAVIS is that it's deeper than HST, sharper than JWST. So at the bottom, you see a mock image of HST versus MAVIS. So you see we're going to reach fainter surface brightness, fainter objects. These are just high redshift galaxies. And then at the top, you see a mock-up of a galaxy redshift 6. So this is the UV rest frame brightness, I suppose. So it's these are two colliding galaxies at redshift 6, and then you see MAVIS can resolve significantly more features than JWST can, and even more than the ELT. So our science case is on arXiv, and there are several main themes: the emergence of the Hubble sequence, resolving galaxy contents, which I've given you a little snapshot of here, star clusters as tracers of galaxy evolution, and the birth, life, and death of stars and planets. So these are our 4 themes for MAVIS. It's a pretty well-balanced science case. What I'll focus on is star clusters specifically. So MAVIS has to deliver a certain level of astrometry. So what is astrometry and why is it challenging? So astrometry essentially comes down to measuring the positions of objects in the sky. There are two flavors. There's absolute, so that's where you have, that's sort of what Gaia does. So there's a background, a world reference frame, but when you're measuring the object in one snapshot, it's not relative to anything else in that image. So that's, for example, like if I was going to measure the position of Barnard's star, there he is. So then we have differential astrometry. So this is a little bit more doable for systems that are not designed specifically for astrometry. So this is measuring the position relative to other objects. So there's a tiny Barnard star, and I just want to measure the distance between the two. So this is easier. And then ultimately what we want to do is combine astrometric measurements from different epochs, so from time 0 and time 10 years later, so that we can actually measure the true motion of the objects in the sky. So now we're going to see Barnard's star move along. There he is. So that's what we want to do. From there, we can recover kinematic and dynamical information of different objects. So several different science cases can use this technique of proper motion measurements. So MAVIS has a goal of 150 micro-arcseconds is the goal, but it must deliver 150 micro-arcsecond precision. So this is the same as the ELT. Again, that's because we operate in the blue, they operate in the near IR, so we're actually complementary in that respect, but it's a challenging goal. So how can we explore whether we'll be able to achieve this goal before we go on sky? So what we want to do is try to predict what MAVIS might be capable of doing before it goes on sky. So to do this, we want to realistically model MAVIS photometry. So this resulted in us creating the MAVIS Image Simulator, MAVISIM. If you have a better name for it, please suggest one. It's gone through a couple different iterations. So it's the first MCAO image simulator that accounts for major AO errors. So we're trying to give astronomers basically try to show them exactly what they'll be getting on sky so that we can test science cases before MAVIS goes up. So we've got several different sources there that go in. Two things to consider are the turbulence conditions. So that's what the sky is actually like. We have some idea of what that's like on Paranal, so we can sort of simulate it at the moment. And then the AO system model, so that's the optics and what kind of correction the AO system will perform. That goes into creating this PSF, which is spatially variable. And then we have several other sources of error. So these are the ones that are kind of unique to the system. There's a distortion term, and the natural guide stars themselves introduce error terms as well. So we call that the sort of error kernel or the error PSF. It's also spatially variable. Ultimately, you want to add some sky characteristics and some detector characteristics to create your final image. So this is what MAVISIM does. Each of these errors are tunable, and you can pull them out or put them back in as you wish. So once we have a MAVISIM image, how do we perform astrometry? So we measure the object centroid. This is a first pass. It's really rough. So that's just sort of like a Gaussian object locator. And then we want to model the PSF to improve precision. So this is the sort of industry standard for doing photometry on AO images. MCO images specifically is you perform PSF fitting photometry. Excuse me. All right. So these are the three errors that I want to mention to you today because they're the biggest ones, and they're the ones we've been exploring as far as trying to understand which one is going to impact MAVIS the most. So the first one is PSF field variability. So if you've ever looked at an MCAO image, you will be very familiar with the field variability that comes out of them, that's associated with them. So both the natural guide star and laser guide star constellations result in a very fun word to pronounce, anisoplanetism. So what anisoplanetism is, essentially it's the fact that your guide star and your science star, so your guide star is a natural guide star or your laser guide star, it's over here. Or sorry, it's right in the center, and then your science object is a bit displaced from that. So what happens is they don't travel through the same turbulence volume. So you can see there's a patch where they don't overlap. So even though you're measuring the turbulence from the reference star, it doesn't completely explain the turbulence associated with the science star. what that manifests as is an elongation of the PSF. So it looks like an oval rather than a circle. Yeah, and so the further you go away from the reference star, the guide star, the natural guide star, the laser guide star, the worse the anisoplanetism is. So this is why the edges of the field in MCO images are so, the PSF is so much worse than the center. So the LGS results in the elongation of the core, the wings, and the NGS manifests in the core. So we've encoded this variability into our simulator right from the start, which makes it more realistic. All right, and so here's two examples of the PSF at different points of the field. So right when you're at the edge, furthest away from the natural guide stars, you get the worst elongation. So this is elongated in the radial direction, and you can see that in the PSF profile. The blue is the perfect AO PSF, the red is the aberrated one. So that suffers from the anisoplanetism. And then as you move closer to the center, your PSF becomes more well-behaved, and the profile starts to converge to the optimal AO correction. The second error I want to talk to you about results from the natural guide stars. So this is called the tip tilt error. So think about tip tilt as if you took your image and you tilted it to the left, or you tilted it towards you, and it just creates a strange sort of distortion. So some of the stars end up looking, defocused, and some of them look, I guess, more in focus than the others. So here's a schematic of the MAVIS field. So the imager is this 30 arcsecond by 30 arcsecond patch. MAVIS will use 8 laser guide stars and 3 natural guide stars. So you can see they're outside of the field, outside of the imager fields, but this gives us a bigger patrol field. So we can find natural guide stars anywhere in here to use. So again, the tip tilt comes from the natural guide stars and how well we're able to measure them to reconstruct the tip tilt error. So it's also, you could call it positional jitter. It just moves the position of the stars in the sky. So it depends on the geometry and the magnitude of the natural guide stars. So the fainter the guide stars, the harder it is to recover the tip tilt. The further away they are from the field, again, the harder it is to recover the tip tilt. So it has the effect of acting like a Gaussian kernel. You could approximate it as a multivariate Gaussian, if that means anything. So it broadens and blurs the image. So here you can see an optimal NGS constellation, and there's an isoplanetism that's stretching the kernels, but you see that they're quite small in the center, right in the middle of that constellation. Here's a worse situation. The more further you move from this guide star, the worse the anisoplanetism is, and the worse the tip tilt is. So that manifests as...
We have 5 minutes left.
5 minutes, thank you. So that manifests as a blurring, which, yeah, is no good. All right. Static distortion introduces, again, sort of like a tip tilt, stretches the image, and it's very important to characterize it. So we want to minimize this distortion in MAVIS, which we have already. Just to give you a hint, we've done GEMS, so that's the only other MCO system with Sky, is 180 milliarcsecond distortion, 9 pixels. We've minimized ours to 44. All right, and here's our map. So there's GEMS, the static distortion, and MAVIS, the static distortion. So these are amplified by factor 3 and 100, so we're doing much better. All right, in the end, we found that the NGS brightness is the dominant source of error. So here's 3 examples of tip tilt constellations, or sorry, NGS constellations, the best, intermediate, and the worst. And in the case of the worst, these are the faintest stars the furthest from the field, but the fact that they're faint is more important than where they are in the field. So brighter stars are better for MAVIS. The next thing we wanted to do was test a science case. So actually use MAVISIM to test a science case before we go on Sky. So we wanted to look for intermediate mass black holes. These are in the mass range 10 to the 3 to 10 to the 5. They're the missing link between stellar and supermassive black holes. One theory is that they can form through runaway mergers. As of yet, no undisputed evidence for their existence in globular clusters exists, but they have been found otherwise in other locations. So here's a MAVISIM image of the cluster 3201 with the IMBH planted in the center. So, and here's an example of the elongation you see for us to try to be realistic. So we simulated a 10-year epoch and then tried to recover the presence of the IMBH via proper motion. So the stars at the center closest to the IMBH will speed up, and you'll see that in their velocities. Here's an image, and here's a little proper motion snippet. So there they are. I'll just play them one more time really quick. So those are the stars moving under the influence of the intermediate mass black hole over 10 years. Okay, so our results from this are really exciting because it shows when we perform the simulation that MAVIS will be able to recover the dynamical signature of this IMBH. We converted the proper motions to velocities. So from there, you bin them and you get something called the dispersion. So if the dispersion shoots up in the middle of the cluster, that's the signature of the IMBH. So when we compare our profile, which is on the right here, so that's dispersion versus cluster distance, so 0 is right at the center, we recover errors in the innermost bin that are very small, 0.23 kilometers per second. These are similar to the errors that Gaia recovers at the edge of the cluster, so under significantly less crowding. Sorry, not the edge, but about 58 arcseconds. So I've showed you that here, the crowding limit is far to the right. So we're surpassing Gaia, and also Gaia hasn't been able to look this far into the center just by virtue of being smaller. And we recovered six times more stars in the cluster center than HST. So we are going deeper than HST, which is exciting. I've also showed you the HST crowding limit here. So HST would not see the turn up in dispersion from the IMBH because it could only see things to the right. All right, so our next step is to look at photometry with MAVISIM. So we want to move to a realistic broadband PSF. At the moment, we're only monochromatic. So the science case that we want to look at with this is looking at star clusters outside of the Milky Way. So we want to push MAVIS to 100 kiloparsecs or more. An example are these Fornax globular clusters around the Fornax dwarf galaxy. These should not exist under the lambda CDM paradigm, so they're great objects to explore. And so we also want to look at different techniques to recover the photometry with MAVIS before we go on sky. So I'll just give you a summary. So what was the motivation? So we wanted to predict the astrometric capabilities of MAVIS and test real science cases before we go on sky. So we've created MAVISIM, which has a GitHub, which is not yet public, but will be public once we get the referee report. And so it's the first simulator that accounts for major MCO errors. So it's more realistic, hopefully, if you want to test your stellar astrometry and photometry cases before going on sky. So right now it looks like the NGS brightness is the most important thing as far as extracting astrometry with MAVIS. So it's not so much the constellation, and even the LGS constellation is less important than the NGS brightness. So we recovered the dynamical signature of an IMBH and the inner 3 arcseconds of a globular cluster center. So, and that's the same precision as Gaia in the outer edge. And Gaia cannot push further inwards than that. And we recovered 6 times more stars than HST. So we are going deeper than HST and to a regime where HST has yet to be able to go. And all of this and more is detailed in a paper that's been submitted to MinRes with the referee report, I am sure, sitting on the editor's desk. So thank you very much for listening. I'll take any questions you have.
Thank you, Stephanie.
Thank you.
Do we have any questions? Feel free to raise your hand or use the chat function. Question from Doug in the chat: when should MAVIS be available?
Yes, good question. So MAVIS, I was just thinking about this morning. I think we're meant to go on Sky 2025. So we're meant to come on just before Mikado Maori. So I think we're aiming for 2025. I should know that off the top of my head, but just have a look.
I was going to make the flippant comment that in terms of a name for MAVISIM, it's an Australian thing, so it has to be an animal, because that's what we do in Australia, is name every astronomy thing after an animal.
Oh, yes. Perfect. I love that. I could do that. Oh, have to come up with some sort of animal acronym. Oops, sorry.
We might be running out of animals between galah, dingo, wallaby, funnel web, taipan, all these things. So I've got a question from Alex G. How bright is good enough for the NGS? Yeah,
so that's a good question. So we want to push MAVIS. So the NGS that I experimented with were between 16th and 18th magnitude in H band. So that's probably the regime where MAVIS wants to work in. We would like to push as far as 17th magnitude in H band, which is actually surprisingly faint. So we're going to use some really fancy new zero renoise detectors to actually do that sensing. But so probably you want to cut it around 16th or 17th magnitude in each band for good results. But even having just one bright star improves your results significantly. So if you've got 2 magnitude 17th, 18th stars and 1 magnitude 15, you're already doing better.
I guess a follow-up question to that would be in terms of the issue with the brightness of the natural guide stars. Have you looked at how the distribution of those on the sky in those magnitude ranges, that are you limited that you can't look at certain clusters because they just aren't the NGSs?
Yeah, so we have yet to test this sort of, I guess you'd quantify that as the sky coverage. So we've yet to quantify the sky coverage for clusters beyond the Milky Way. But I think all the Milky Way globular clusters should be fine as far as having guide stars in the field. And because we can push fainter, that allows us to pick up ones that GEMS might have missed. Yeah, so that's a good question. We do have to deliver 50% sky coverage. So that means that anywhere in the sky, you should be able to find a guide star. Yeah, at least 50%.
I guess there are a lot of 17th magnitude stars out there.
Yes, yeah, exactly. And so, yeah.
Daryl suggesting Quokka as the acronym, or the name. I'm not sure whether we've done that yet. Any other questions?
I might also put a call out just to people in the audience. If you have science cases you would like to test, please shoot me an email, because we're always looking for more science cases to test. And if there's a way we can do that with MAVISIM, it'd be great.
Okay, looks like we're out of questions. So thank you to Stephanie and Jake for their great talks.